Welcome everyone to today's Explainer. Today, we are setting the stage to explore something we all literally rely on every single second of our lives, yet we hardly ever think about it. We're talking about the massive, often completely invisible physical realities and intense engineering challenges of our electrical grid. We're going to pull back the curtain on how electricity actually moves, the raw physics of keeping the whole system stable, and the life-saving mathematics that engineers use to protect us when things inevitably go wrong. So, let's jump right in.
Here's a quick look at our roadmap for today's Explainer. We'll start with the electricity supply chain, dig into why high voltage matters, look at the renewable energy challenge, cover grid inertia and stability, and finally wrap up with substation grounding and safety, plus how we calculate fault currents.
All right, Section 1, the electricity supply chain. Okay, let's dive into this. How does power actually get from those massive generation facilities all the way down to our homes and businesses? Well, it's kind of an incredible journey. Starting at the very beginning, you have your power generators, a coal plant, a wind farm, or a hydroelectric dam. Now from there, the power doesn't just flow straight to your living room. It first travels through step-up transformers and hits the high-voltage transmission network, which spans vast geographical regions. Eventually, it reaches step-down transformers at sub-transmission and distribution networks, finally making its way to commercial, residential, and industrial end users at the very end of the line.
If we actually look at the specific voltages on that journey, it's pretty wild. Power plants generally produce electricity at relatively low voltages, typically sitting somewhere between 5 and 34.5 kilovolts. But to move that power efficiently across the country, generation voltage has to be stepped up significantly for the transmission phase. We're talking 69 kilovolts and well beyond. Finally, during the distribution phase, it gets stepped back down below 34 kilovolts so it can safely travel down your street.
Moving on to Section 2, why high voltage matters.
So you might be wondering, why do we need extreme voltages and those giant towering transmission structures in the first place? Well, it's because a long transmission line is absolutely not a simple lumped circuit. You can't just use basic circuit algebra here. A voltage change at one end doesn't just instantly teleport to the other side. It travels as a wave at nearly the speed of light, which takes real, measurable time. Because these lines are so long, they have distributed parameters continuously along their length. Series resistance from the metal, series inductance from the magnetic field, shunt capacitance from the electric field, and shunt conductance. This creates a specific, super important point called surge impedance loading, or SIL. Basically, if you load a line at exactly its SIL, the reactive power produced by the capacitance perfectly cancels the reactive power consumed by the inductance. The result? The voltage stays completely flat end to end. If you load it below SIL, the voltage actually rises toward the far end. Load it above, and it sags. That's why planning engineers treat lines as voltage limited below SIL and thermally limited above it. And quick check, how do you raise a line's SIL to push more power without rebuilding the towers? You bundle the conductors. Running 2 or 4 subconductors per phase increases what we call the geometric mean radius, or GMR. That lowers inductance and raises capacitance, pushing the SIL higher. It's a direct design trade-off with the geometric mean distance, or GMD, between the phases. This is exactly why those massive 400 kilovolt plus lines almost always use bundled conductors.
Section 3, the renewable energy challenge.
Right now, we are seeing a massive, unprecedented influx of renewables into the system. In many modern grid studies, solar PV sits around 35% and wind power makes up about 30% of renewable penetration. Now, while these sources are obviously fantastic for the environment, we have to talk about the physics. Their large-scale integration completely changes the electrical behavior of the grid. We are essentially swapping out the very types of machines that power our world, and trust me, the grid feels that difference immediately.
Section 4, grid inertia and stability. So the crucial point is the sheer difference in how traditional versus renewable power actually connects to the grid. Traditional power plants rely on synchronous generators. These are literal, massive, incredibly heavy rotating steel turbines. They have huge physical momentum, or inertia, which naturally acts like a giant shock absorber, instantly resisting any sudden changes in the grid's electrical frequency. But modern solar and wind, they are inverter-based resources. They have zero heavy rotating mass. They have very low inertia. When you take away those heavy spinning generators and replace them with static solar panels, you get what engineers call weak grid conditions.
And the literal, mathematical rules of the game for grid stability are defined right here by the swing equation for generator dynamics. See that h in the denominator? That represents the system's inertia. As we add more solar and wind, that h value drops, and because h is on the bottom of the fraction, as it shrinks, the rate of change of frequency, that df dt over on the left, gets larger and faster. Basically, the grid becomes highly vulnerable to sudden, violent frequency disturbances.
And this brilliantly illustrates the real-world impact of that dropping inertia. In high renewable systems, low system inertia now accounts for a staggering 35% of overall grid stability issues, followed closely by generation variability and voltage instability. This disappearing inertia is completely forcing the hand of grid engineers. They're having to invent entirely new mitigation techniques, like grid-forming inverters and virtual inertia control, literally just to keep the lights on and the system stable.
Moving into Section 5, Substation Grounding and Safety.
Now, I want you to consider a pretty terrifying scenario for a moment. What actually happens when the system faults? Like, what happens when a massive lightning strike hits a transmission line, or heavy insulation fails, or a huge switching surge occurs? Where does all that raw, destructive, high-voltage energy go? And more importantly, how is it safely managed so it doesn't just destroy the equipment or, God forbid, kill the utility workers standing right there?
Well, when a fault happens, it generates what engineers call the symmetrical ground fault current. Put simply, this is an incredibly intense, immediate release of electrical energy in the very first fraction of a second after a fault initiates. To handle this, substations absolutely must have a robust, completely invisible system to catch this violent surge of current and dissipate it harmlessly into the earth.
And that brings us to the hidden reality beneath every major substation. It's a literal life-saving infrastructure. Long before they ever pour a single ounce of concrete or install those giant transformers, engineers bury an intricate web of horizontal copper meshes and drive deep vertical electrodes straight down into the soil. This entire ground grid is specifically designed to grab that massive fault current and forcefully disperse it deep into the earth before it can cause any havoc above ground.
Finally, Section 6, Calculating Fault Currents.
Now, designing that underground mesh is absolutely not guesswork. According to strict IEEE standards, engineers must account for a staggering number of variables. They literally have to measure the exact soil resistivity, as in how well the local dirt conducts electricity. They have to factor in the thickness of the crushed rock sitting on the surface, the total area of the grid, exactly how deep the copper is buried, and precisely how many fractions of a second the fault is going to last. I mean, in substation design, the electrical properties of the dirt beneath your feet are quite literally a life-or-death metric. All of those intense dirt and layout variables feed into highly complex formulas to manage two very critical threats: mesh voltage and step voltage. If the underground grid isn't designed perfectly, a massive fault can cause the voltage of the actual ground surface to dramatically spike. Step voltage is literally the voltage difference between a person's 2 feet as they take a step. Engineers use these math equations to ensure the ground potential never rises so high that it electrocutes an operator who's simply walking across the gravel during a fault event. It's mind-blowing when you think about it.
So ultimately, the core takeaway from all this source material is this. The electrical grid isn't just a bunch of wooden poles and dumb wires. It is a stunningly intricate, beautiful balance. It relies on massive macro infrastructure spanning entire continents, the physical momentum of giant spinning machines, and microscopic, deeply complex safety calculations operating in the dirt right beneath our feet, all working together to keep everything safe and stable. Which leaves us with this final, provocative thought. As the world rapidly pushes toward 100% renewable energy, systematically removing those heavy spinning generators and altering the very physics of how our power actually moves, how will the incredibly delicate math of grid stability and human safety have to evolve to meet the challenge? It is a truly fascinating engineering frontier. Thank you so much for exploring this explainer with me today. I really hope you now look at the power grid with a whole new level of appreciation.